This is section 3.1 on exponential functions. Sketch and analyze the graph of f of x equals 4 to the x. Let's use an xy chart to do this. We have x and y. Let's go from -3 to 3. So we have -1, 0, 1, 2, and 3. When we plug -3 in, we really have 4 to the -3, which is equal to 1 over 4 to the third, which is equal to 1 over 64. 1 over 64. When we do the same process, we get 1 over 16, then we get 1/4. Anything to the 0 power is 1. Then we have 4, 16, and 64. So -3, 1/64 is right there, approximately. Then this one's probably a little higher, and then we get 1/4 is a little higher. We get 0 to 1, and then when we plug 1 in, we get 1, 2, 3, 4. And then 16 is kind of off the map if we're going to go by ones. So this is what the graph looks like. And it will go very steep, but it will go to the right forever. The domain is -infinity to infinity. There's nothing we can't plug in. There's no radicals and there's no denominators. The range is 0 to infinity. It is leveling out to 0, so we have an asymptote at y equals 0. We have a y-intercept at 0, 1. The end behavior is the limit as x approaches infinity of f of x is infinity, and the limit as x approaches -infinity is 0. So this is leveling out to 0 as we go to the left. This function increases the entire time, so -infinity to infinity. Sketch and analyze the graph of f of x equals 5 to the -x. Now that's the same as 1 over 5 to the x, and sometimes you will see it as 1 over 5 just raised to the x in general. But 1 to the x is just 1, and then you have this 5 to the x. Let's use an xy chart to graph this one as well. We have -3, -2, -1, 0, 1, 2, and 3. When we plug -3 in, that brings this all the way back up to the top, and we get 125. 2 gives us 25. 1 gives us 5. Now anything to the 0 is 1. Then we get 1/5, 1 over 25, and then 1 over 125. So -3 gives us way up to 125. -2 gives us 25, and finally when we get to -1, that's going to be 5. 1, 2, 3, 4, 5. 0 is 1, and then we have 1/5, 1 over 25, and then it's so small we can barely graph it. But you can see as we go to the right, it's going to be leveling off to 0. And then here is the shape of the graph. Now if you look at 5 to the x, when you have 5 to the -x, that negative is on the inside, and these are reflections over the y-axis. So 5 to the x would look like this as we go to the right, and 1/5 to the x is going down. The domain is -infinity to infinity. The range on this one, just like the other, is 0 to infinity. The intercepts, we have 0, 1, we have a y-intercept, asymptote, so y equals 0. And the end behavior is the limit as x approaches infinity of f of x equals 0, and the limit as x approaches -infinity of f of x is infinity. And this function decreases the entire time as we go left to right. Key concept: properties of exponential functions. Exponential growth. When the base is bigger than 1, then it's exponential growth. For example, 5 to the x or 7 to the x. When the base is between 0 and 1, or in other words a fraction, then this is exponential decay. For example, 1/2 raised to the x. Or if you have 3 to the -x, that's considered a fraction because you can change it to 1 over 3 to the x. Use the graph of f of x equals 1/2 to the x to describe each transformation. Well, let's look at 1/2 to the x. If you have 0, that's 1. 1 is a half. 2 is a fourth, 3 is an eighth, and then negative 1 would be 2, negative 2 would be 4, and negative 3 would be the one that's all the way up to 8. So this is leveling out as you go to the right, and then as you go to the left, this is shooting up to infinity. G of x equals 1/2 to the x plus 1. This plus 1 is on the inside of the function, so this is left 1. Now we're going to take all these points and we're going to move them all to the left 1 unit. So the half gets moved to the left and then it just levels off to 0. So here's the graph of 1/2 to the x plus 1. It should be a nice smooth curve leveling off to 0. 1/2 to the negative x, this negative is on the inside, so this is a reflection over the y-axis. So now we'll take the black and we will reflect this over the y-axis. So this 1 goes to 1 over here. Whoops, I missed. This should actually be over there. Forget that point right there. This stays, and then we have a half and a fourth, and it's leveling off to 0 as we go to the left in this case. Right here, and then shooting off to infinity. On the third graph, this negative is on the outside, so we have reflect over the x-axis. And then the 2 on the outside means we're going to stretch vertically. So stretch vertically by 2. So let's take the black and reflect this over the x-axis. So the 4 goes down to negative 4. The 2 goes down to negative 2. 1 goes to negative 1. And then we have the half and the fourth, and it's leveling off to 0. But then we have to stretch all this by a factor of 2, which means we take all of the y values and double them. So the 4 goes to 8. 5, 6, 7, 8. The 2 goes to 4. The 1 goes to 2. The half goes to 1. And then it starts leveling out to 0. Let's try. There we go. Something like that. The most commonly used base is the irrational number e, called the natural base. E is the limit as x approaches infinity of this function. And the closer you get to infinity with this function, the closer we get to 2.718. That's usually the number we use for e. Use the graph of f of x equals e to the x to describe each transformation. Then sketch the graph of the function. Well, if we have e to the 0, that's 1, and e to the 1 is 2.718. So let's say about right there. It levels off to 0 as we go to the left, and it shoots off to infinity as we go to the right. G of x equals e to the 3x. Well, this 3 is on the inside of the function, so we're going to say that this shrinks horizontally by 1/3. Now we'll take all the x's and multiply by 1/3. So this 1 goes over here to 1/3, this one stays at 0, and this one would be over here at 1/3. And then it shoots off to infinity and then levels out to 0 on the left. This negative on h of x is on the inside, so this is a reflection over the y-axis and then down 1. So we say reflect over the y-axis and down 1. Let's take the black and reflect it over the y-axis. That's over here. The 0 stays here, and then it'll level off to 0, but then we need everybody down 1. So down here, and then 1.718. And now the horizontal asymptote has been bumped down to -1. So we'll show that the asymptote has actually moved. So it's going to level off, and over here it's going to shoot up to infinity. Key concept, compound interest formula. If a principal P is invested at an annual interest rate R in decimal form, compounded n times a year, then the balance A in the account after t years is given by the amount equals the principal times 1 plus the rate over the number of times compounded raised to the nt, where t is time. If a principal P is invested at an annual interest rate in decimal form compounded continuously, then the balance A in the account after t years is given by the PERT formula, principal times e to the RT. Mrs. Salisman invested $2,000, which is now the principal, into an educational account for her daughter when she was an infant. The account has a 5% interest rate. If Mrs. Salisman does not make any other deposits or withdrawals, what will the account balance be after 18 years if the interest is compounded, let's say quarterly? So we're looking for the amount in the account that'll equal to $2,000 times 1 plus the rate, which is 0.05, over 4, because this is compounded quarterly, 4 times, raised to the 4 times 18. The t is 18 years. Let's go to the calculator. We have 2,000 times, we have 1 plus 0.05 divided by 4, and we're going to raise that to 4 times 18. And we have $4,891. $4,891.84. Now with monthly, everything is the same except n is going to be 12. So we have 2,000 times 1 plus 0.05 over 12 raised to the 12 times 18. Well, we can go second entry, and then we can change the 4 to a 12. So maybe we insert the 12 and then delete out the 4. Then go over to the 4, insert 12, and delete out the 4. We have $4,910. So $4,910.02. With daily, we have the same thing again. So we have 2,000 times 1 plus 0.05 over 365 raised to the 365 times 18. Now we'll go second entry again. Insert 365. So we'll do insert 365 and we'll delete out the 12. And we'll do that again over here. So we'll insert 365 and delete out the 12. We have $4,918.90. With continuously, it's a slightly different formula. We have principal 2,000 times e to the 0.05 times 18. Let's enter 2,000 times, the e is the second function of natural log, and we have 0.05 times 18 years. That's going to be $4,919.21. Exponential growth or decay formulas. If an initial quantity n sub 0 grows or decays at an exponential rate r or k as a decimal, then the final amount n after time t is given by the following formulas. Exponential growth or decay, we have n equals n sub 0, 1 plus r to the t. If r is a growth rate, then r is greater than 0. If r is a decay rate, then r is less than 0. Continuous exponential growth or decay is that PERT formula again. A state's population is declining at a rate of 2.6% annually. The state currently has a population of approximately 11 million people. If the population continues to decline at this rate, predict the population of the state in 15, and this should probably say in 15 years. So the population is going to be equal to the initial population, which is 11, times 1 minus 0.026 raised to the 15. We have 11 times 1 minus 0.026 raised to the 15. And that is 7.409, so 7.409 million people. Now we wanted this to be a minus because this percentage right here is a rate that is declining. A state's population is declining at a rate of 2.6% continuously. The state currently has a population of approximately 11 million people. If the population continues to decline at this rate, predict the population of the state in 15 years. So the number of the people will equal 11 times e to the negative 0.026 times 15. We have 11 times e to the negative 0.026 times 15. And that is equal to 7.448 million people.